Hello, this is part one of a three-part video series on the topic I recently published, a journal article recently published and presented at the Addis Continental Institute of Public Health. The motivation for the three-part video is the fact that I did not have enough time at the time of the presentation at the Addis Continental Institute of Public Health to cover all grounds regarding data, methods, issues, recommendations, conclusions, body of research. Just not enough time. To make it worse, I was 5 to 7 minutes late in traffic, traveling from, the Addis Ababa traffic, traveling from Bole to Ayat. So I was late. Not too much, 5 to 7 minutes, which did not cut into my presentation time, which was scheduled for 30 minutes. It ended up cutting into the discussion time, which was also scheduled for 30 minutes, but did not last 30 minutes. At that point, on that day, I made a decision, a promise to myself, a resolution to do a video series to cover grounds that I was not able to cover due to shortage of time. But at this stage, I need to present a disclaimer. I mentioned my place of work in the state of California. I also mentioned the location for the presentation. But having said all of that, I would like it known that I am solely responsible for the content of this video. The materials presented here have not been reviewed or approved by my place of work here in the state of California or the Addis Continental Institute of Public Health, ACIPH, where I presented it. They are in no way liable or responsible for inaccuracies or omissions, nor do they vouch for the validity of the data presented or methodologies followed. I would like to start by introducing to you a few websites. You might have seen them before. This is my website, www.ethiodemographyanhealth.org. I call it an online book, except that unlike the traditional book, this is an updatable book. Updates have happened in the most optimistic scenarios on a daily basis and weekly basis. But in most situations, updates might have a frequency of a month, so monthly is the better way to describe the timetable rather than daily and weekly. Monthly is a better way to describe the timetable for updating this website online book. To open the cover, just click here. It takes you to the content page. The three part videos will be linked here as video 1, video 2, and video 3, and also scripts from the R programming that I will be using today in today's video will be linked here in a PDF format, meaning that the user is able to copy the scripts and use them on any computer that has R Studio. I did not upload the R codes themselves directly because opening them was going to require having a computer with R Studio installed. So to save the user a lot of heartache and headache, I will upload it in a PDF format. The next website I will introduce to you is the World Health Organization website, in particular the social determinants of health, which is social determinants of health is a core concept in the field of public health and in public health research. And I'll be introducing elements from the social determinants of health in possibly today's presentation or in the next one. The next website I'll introduce to you is the DHS website, Demographic and Health Survey Program website. This is where all the data for demographic and health surveys around the world, a number of countries, I believe it's about 90 countries in the world that have participated over the years in the demographic and health survey, including Ethiopia. And this is the data repository. Next, I will introduce to you the location, the website where my article was published. It was published by the Canadian Center for Science and Education, Journal of Geography and Geology. The topic again, the social geography of women's health attitude towards wife beating in Ethiopia, a contribution towards proper application of spatial statistics. The inclusion of the word proper suggests that I have observed improper applications of spatial statistics. Yes, indeed, I have observed numerous instances of improper applications of spatial statistics to the Ethiopian demographic and health survey data. So this is the contents page for the 3-part video series, objectives of the video series, background, in particular, backgrounds in GIS for public health, and more specifically, spatial statistics in public health. The content includes improper application. I've already tried to whet your appetite for what I have to address, or as a response to what I thought was improper application of spatial statistics to Ethiopia's DHS data. Also included in the contents is Ethiopian women's attitude towards wife beating, and in particular, testing of the data, the spatial data on women's attitude. This is at sampling cluster level for 643 sampling clusters where women participated in the 2016 DHS survey. And I will introduce in the three-part video a very, very important application, relatively recent, relatively new. It's called the Geographically Weighted Regression Methodology, or GWR. And the three-part video will end with a summary and discussions. So the objectives: 1, to provide brief backgrounds about GIS and use of GIS in public health. 2, bring attention to improper applications of spatial statistics to Ethiopia's Demographic and Health Survey data, EDHS data. 3, show simplified steps for assessing whether a variable is suitable for spatial ordinary least squares, OLS, linear regression, is a variable of interest. In particular, the Y variable, the dependent variable, the outcome variable, is that suitable for the application of OLS? And the steps that I'll be sharing would use the 2016 ADHS data on women's attitudes towards wife beating. Finally, I will highlight an application, a geographic information system tool known as the Geographically Weighted Regression, GWR, by using as an example unweighted percentages of women who responded that wife beating was okay. So that's the Y variable, the outcome variable. And the independent variable would be their educational status. Background: Geographic Information System, GIS. What is GIS anyway? GIS is a computer-aided database management system that organizes and stores large amounts of multi-purpose data. It's a mapping and spatial analytics technology. Spatial analytics is, I have an asterisk against it. It is explained as the process of examining the locations and attributes and relationships of features in spatial data through overlays and other analytical techniques in order to A, address a question, a research question, or B, gain useful knowledge. Spatial analysis extracts, in doing that, it extracts or creates new information from spatial data. Here's the source indicated for this quotation for those who are interested. Background continues. Latest trends in GIS. Real-time data, as in like traffic monitoring in real time. Very popular in most metropolitan cities of the developed world. For me, the closest one to me would be the San Francisco Bay Area traffic. Real-time data. Miniaturization of sensors, meaning sensors becoming more and more small. 3 is GeoAI, artificial intelligence in geospatial analysis. Self-driving vehicles are AI-driven technologies. Smarter cities, digitally interconnected parts of cities and city services and city functions. 3D and digital twins, machine learning, artificial intelligence. Now all the way to number 9, sustainability, especially in the face of climate change and all the serious risks humanity is facing, including health risks, disaster mitigation at number 10, and response to disasters. Workflow automation is big now in the current trend. At number 12 is light detection and ranging LiDAR. 13, geospatial augmented reality. And the last three have to do with software as a service, SAS, image raster analytics, which is really not a new trend. It's been around a long time. And what's newer, a lot more than that, is number 16, which is GIS increasingly moving to the cloud for storage, data storage, and also efficiency of computing in the cloud. Background continued, GIS and public health. A little bit introduction to the field of public health itself, having introduced what GIS is. So it's GIS in public health. We now know more or less what GIS is and the latest trends in GIS. But how about public health? What's covered in public health? Well, public health is dedicated to improving the health of populations. So it works on a population level rather than individual level. It's also more focused, almost exclusively focused on prevention when compared to treatment. Public health is operationalized mainly in a governmental setting, rather than private enterprise context, which means that public health falls naturally within the domain of health sciences, requiring spatial analysis, because disease occurrence is not the same in one place to the next, from one place to the next. That difference in disease occurrence or spread from one place to the next automatically implies differences in spatial distribution, which requires spatial analysis to figure out or comprehend. Finally, GIS is amenable to spatial statistics because GIS allows potentially transformational capabilities for public health efforts by providing a digital lens, is all digital, for exploring the dynamic connections between people, their health and well-being, and the changing physical and social environments. Background continued, GIS and public health. These are some items I selected as the usefulness of GIS to public health practitioners, about 7, 8, 9 items. First one being the optimization it provides. Public health practitioners use GIS to optimize data collection and management, including data collection on the field. For example, to monitor outbreaks and where disease is headed in space. Next one, to strengthen data analysis by bringing in a host of data, merging data, and looking at relationships between health and potential, or health and disease, and potential causes of compromised health or spreading disease. Next, GIS helps strengthen infrastructure support for those institutions interested in monitoring outbreaks. GIS allows mapping of epidemic and disease dynamics in almost real time. The GIS helps in quickly explaining phenomena as they happen, and also for targeting responses. GIS is key in rapidly communicating information through maps, because maps are images, and as the cliche goes, a picture is worth 1,000 words. GIS helps in monitoring changes over time. GIS is crucial in planning and in monitoring interventions, especially when it comes to eradication programs, for example, malaria eradication programs. And finally, GIS is key in emergency preparedness. To focus specifically on spatial statistics and the tools that are commonly applied in the field of spatial statistics, I'm highlighting about 4, the most commonly used ones, starting with SATScan. If you're interested in SATScan, go to this website, www.satscan.org. Simple as that. Next is GIS. My 3-part presentation is based on this second one from ESRI, ArcGIS Pro based Spatial Statistics Toolbox, and the hundreds of tools in that toolbox. Next is S+ or R programming. R programming is increasingly becoming a very popular platform for GIS spatial analytics. In recognition of this, ESRI has created what it calls Bridge ArcGIS Bridge, ArcGIS Bridge, created by ESRI. And the last one is QGIS. This is open source, free application. If you're interested, the website is www.qgis.org. Now to improper applications of spatial statistics to Ethiopia's demographic and health survey data. The main form of improper application is using spatial least square regression in situations where there is clear evidence that the data is spatially autocorrelated. In environments where there is clear evidence that the data is spatially autocorrelated, you cannot use OLS, ordinary least square. It would be improper to use ordinary least square regression in conditions, in situations where there is spatial autocorrelation of the outcome variable or the independent variable or both. So in quotation it says, whenever there is statistically significant spatial autocorrelation of the regression residuals, the OLS model would be considered misspecified, meaning unfit. Consequently, results from the OLS regression are unreliable. Be sure to run the spatial autocorrelation tool on your regression residuals to assess this potential problem. So the source for this quotation is ESRI itself, ArcGIS Pro. At this point, this would be a great place to show you a short video to bring this point home. A video is entitled Spatial Autocorrelation.
This video is about spatial autocorrelation. It will cover the first law of geography and ways of measuring spatial autocorrelation. What is the first law of geography? A famous American-Swiss geographer named Waldo Tobler wrote the first law of geography, which states, "Everything is related to everything else, but near things are more related than distant things." Geography is very much the study of the relationship between phenomena in space, and the vast majority of natural phenomena closely relates to the things closest to it. For example, the climate in Washington, D.C. is much more similar to the climate in Baltimore and less so to the climate of Los Angeles. Tobler's law provides a simple introduction to a crucial concept in geography, spatial autocorrelation. Spatial autocorrelation examines how similar one data point is to other data points around it, to understand if phenomena relate in space. Positive autocorrelation leads to the clustering of data points. Perfect clustering would look something like this, with like data sticking closely to like. Negative autocorrelation leads to the dispersal of data. Perfect dispersal would look something like a chessboard, where every point is completely surrounded by features unlike it. Perfect negative autocorrelation is incredibly rare in the natural world. A spatial autocorrelation of 0 indicates randomness and that the locations of data points are not related in space. Spatial autocorrelation explains a lot of behavior in geography, and it is very important to take it into account when doing geographic analysis. Sometimes, though, spatial autocorrelation can actually interfere with data processing. Many important statistics assume that all data is randomly distributed, and having internal relationships between the data can cause non-negligible interferences in modeling behavior and calculating important statistics in the dataset. In conclusion, spatial autocorrelation helps us understand how data relates to itself in space. It is measured on a scale from positive to negative, and it is crucial to know the spatial autocorrelation of a dataset when trying to understand patterns in the data. Thanks for watching. I hope you liked my video.
Improper application of spatial statistics to EDHS data continued. So applying OLS in conditions of the presence of autocorrelation is not the only problem. I have identified a total of 5. So first, application again of bi or multivariate global, which is countrywide, like for the entire Ethiopia, ordinary least square regression in situations of high local variability. So in situations such as Ethiopia's, where the country is very diverse, everything varies, things are not the same everywhere. To try and come up with a single coefficient, a global coefficient for all of Ethiopia, using ordinary least square regression is just not proper, because Ethiopia cannot be described, the entire country cannot be described using a single number or coefficient, or beta coefficient, or intercept, or r squared. Number 2, we already seen this, went over this, quite a few times. Number 2, application of OLS to spatially autocorrelated response variable y. Number 3, lack of testing for multicollinearity of the chosen independent variables. Are the independent variables independent of one another, as is required in classic assumptions in statistics? Independence from one another. If they are not independent, you have conditions of multicollinearity, meaning the x variables are related to one another, which leads to model overfitting. Number 4, combining the use of spatial and non-spatial statistical methods. So there's the traditional statistics, there's spatial statistics. They use similar but not exactly identical approaches and techniques. Without warning, some studies combine the two, and not telling the authors which one is just from the regular statistics and which part is from spatial statistics. No warning, no differentiation, no delineation. Finally, publishing contradictory results from different spatial statistical applications. In the previous slide, I showed you the various tools available to you to do spatial statistics. And sometimes when you use two, the results you get may not be the same. One could contradict the other instead of supporting the other. It would be wrong to publish both contradictory results as valid. So that is one observation I have come across. Here is a very good example of an improperly applied statistical method to Ethiopia's demographic and health survey data. The finding, according to the authors, their main finding was that the data was clustered. So the study found a special clustering, meaning autocorrelation, of domestic violence cases in Ethiopia with Moran's I value of 0.26. What is Moran's I? I'll introduce that to you. A z-score of 8.26 and a p-value of 0.001. So, given this finding, the validity, this is my observation, this is what I'm saying, the validity of the following additional results is highly questionable. The result says a regression analysis identified low economic status, partner alcohol use, witnessing family violence, marital controlling behavior, and community acceptance of wife beating as significant predictors of domestic violence in Ethiopia. And it goes further on to say that women living in communities with high acceptance of wife beating were 1.4 times more likely to experience domestic violence than women living in communities with low acceptance of wife beating. So on the face of it, on the surface of it, these findings appear reasonable, but what they're telling you is domestic violence is linked or is associated with these other variables in this way. Unfortunately for the authors, what is being neglected here is that in the presence of clustering, that's the first finding, in the presence of clustering, a high level of domestic violence in location A might be related to a high level of domestic violence in location B if those two locations are contiguous. And that's spatial autocorrelation. In this case, if they are contiguous and spatial abuse is high in both, before you ask the question, are they related to marital controlling behavior or partner alcohol use? Before you do look at that relationship, you ask the question, are the high levels in the two locations A and B correlated with each other? Most likely they are, meaning Y is correlated to itself. Y correlated with itself. More problems with this study. First of all, I have a better graphic of the problem I've observed with this study. Actually, I have a better graphic to show you the problems. Okay, better graphic. So this is a better graphic. On the top left is the Y variable. It's a composite index. Composite index. Meaning it's composed of a number of variables. Actually 3. Partner drinks alcohol. The interviewee witnessed family violence. And also interviewee's attitude toward interpersonal violence, IPV. So all of these are crushed some way, some fashion, to produce a composite index, which is the outcome variable Y. That's problematic. Because if you look at to the top right, partner drinks alcohol, classified as yes or no. And the middle variable, witnessing family violence, classified as yes or no. But the third one, attitude toward interpersonal violence, there are 5 different scenarios for that. Is it okay? Women being asked, is it okay for a husband to beat his wife in these 5 scenarios? A, she goes out without telling him. B, neglects the children. C, argues with him. D, refuses to have sex with him. E, burns the food. Now, if a woman answered yes to 4 out of 5 in the third variable, here, yes here, 4 out of 5, yes here, and yes here. Compare that woman to a woman who answered yes just 1 out of 5 here, not 4 out of 5, just 1 out of 5 here. And then a no here and a yes here. How are you going to distinguish and create a composite picture for that woman and turn that into a Y outcome variable? This is very confusing. That's on the top left, top right is on the outcome variable, the Y variable side. And then on X variables, the independent variables, they're further divided into 3. The individual level, the household level, and the community level. So a total of about maybe 12, 13 variables. No testing to see if any of these 13 X variables are correlated with one another. No multicollinearity test. Also, this scheme, this framing, assumes that the individual level attribute can be separated from the household level attribute, can be separated from the community level attribute. That appears flawed on its face because individual attitudes are usually shaped and are a function of community level attitudes. So they're highly interrelated. The individual is very highly interrelated with the communal, meaning there is multicollinearity. Finally, to the results. The map you see here is the result that identified clusters of elevated spousal abuse occurrences. That's one result. I am not showing it in this slide, but there is a completely different result centered in the south, the Dabub Behairasab area. It's centered. High elevated spousal abuse is in the south, not northwest, but in the south from the statistics. I'm not showing that in this slide, But there you have it. So this is just one example, and there are a number of studies, where I have observed similar issues. So what I was saying in the previous slide was this. What if spousal abuse between partners, a husband and a wife, isn't just a reflection of alcohol use or family history? What if it's just a function, is at least also a function of abuse being high in the neighborhood? That was the question I was asking. Another way to explain that is using this slide over here. This is just the second example. In this case, let's assume that these numbers represent cholera incidences per thousand. In the first graphic here, a location with the highest incidence, 84 per thousand, is right next to another location, or a location with the second highest, 83, in this whole scheme, is right next to a location with the highest. A location with the third highest incidence per thousand, 78, is right next to the highest. A location with the fourth highest, 75, is right next to the location with the highest. So in this case, a researcher could try and relate cholera incidences to, let's say, water sources, or population density, or migration, or availability of sanitary services, proper disposal of waste, all of those independent variables that we might suspect could explain the occurrence and spread of cholera. A researcher might be tempted to look into those. But first, what if it's mainly the location of a place? For example, this location here is far away from this one, and the incidence is much, much smaller. What if it's just the function of proximity, the function of distance? What if it's just spatially autocorrelated? That's the question. Here is a third example. So again, the first example was the study on domestic abuse as a outcome, and a number of independent variables, personal level, household level, community level, as independent variables. That was one example. And the last example I shared with those tables was cholera outbreak per thousand. And this is yet another example, a different way of stating what I've been stating. So in this case, on the Y scale is upper respiratory infections. Okay. Instead of cholera, think of the numbers in the table as upper respiratory infections per thousand. And then on the x-axis, you have altitude. So as you can see already, the data is clustered. Low upper respiratory infection is associated with occurrences of low altitude, and high upper respiratory infection, like you see here, is associated with high altitude. low respiratory infection, low altitude, high respiratory infection, high altitude. Now you could try and relate, a researcher could, in a hurry, start looking at the role of crowding, for example, or is healthcare available in the area, or has the community received vaccination? For example, if this is upper respiratory infection among children, have they been vaccinated? So a researcher could, in a hurry, start looking at those independent variables in the hope of explaining the pattern of upper respiratory infection, where the main correlate appears to be altitude, meaning the location. Low altitude location means low incidence. A location B that is right next to location A and a low altitude would have low incidence of upper respiratory infections. So Y being related to Y. What should a researcher do then before setting out to conduct spatial statistics? What should a researcher do? The researcher should test for the presence of spatial autocorrelation. Test for the presence of spatial autocorrelation. And there are two ways to do that. There are more than two, but I'll just share two. One is called the residual versus predicted plot method. The second one is called the global Moran's I statistic. So first, the residual versus predicted plot, meaning you plot the residuals. What is a residual? So in ordinary least square regression or in some other type of regression, you have the y variable, which is the outcome variable, and you have independent variables. The x, there could be just 1x, x1, or 2, x2, or 3, x2, x1, x2, x3. So it would be y equals beta naught plus beta 1 x1 plus e, the error term. E, the error term. What is e? E is the difference between actual y, observed y, and predicted y. Another name for e is residuals. So one way to test for the presence of spatial autocorrelation is just to test the residuals. Put the standardized residuals on the y-axis and put the x, any one of the x's, or the predicted y on the x variable. Okay, so what kind of plot would be a violation of the spatial autocorrelation rule? Well, 1a, if the relationship is not linear, that's just for the overall y versus x. But when it comes to residuals, classic statistical assumptions hold that the residuals should be independent. Okay? Classic statistics also demands homoscedasticity of residuals. Homoscedasticity of residuals. What does that mean? Okay, so let's assume you have this plot here, and these are the dots are your residuals. Some are negative, some are positive. Okay, negative residuals standardized, positive residuals standardized. This is the error term. Homoscedasticity means And by the way, the total sum of residuals is 0. Okay? The total sum of residuals is 0, which is represented by the horizontal line here. So homoscedasticity means the distance, the average distance of the residuals below and above the line should be the same. The average distance of the most distant residuals, okay, the most distant negative residuals, that distance should be about the same as the distance from the line of identity of the positive residuals. So that's what you see here. That's what you see here. So there is homoscedasticity, in fact, the very perfect one in this example. So this plot gets a check mark. A researcher trying to use such a variable as an outcome variable can go ahead and do spatial statistics provided that the x variables, these ones, are not correlated with one another. So this one passes. Okay? Now, the second one is a different scenario where the residuals are mostly positive when the predicted value, or x, is low. They're, again, mostly positive when the predicted value, or x, is high. But they are mostly negative when the predicted value, or x, is neither high nor low. This one fails. Okay? The third scenario is where the distance of the residuals, both on the positive side and the negative side, increase with an increase in the value of x or increase in the value of predicted y. This one also fails. Now back to the slides I used at the Addis Continental Institute of Public Health. I shared what the data sources were, and I also shared what application I used for processing the data. In this video, I will share both the details of how I downloaded the data and also the details of how I did the R programming. So first, about downloading the data. I am going to log in to the DHS website. I believe that I have an email already saved. And I'm going to sign in. Voila, I'm in. So prior registration is required. You get to use password of your choice. I have registered, I could have registered many projects. I only registered one. I gave the name Ethiopian Demography and Health. Okay. And you can register as many countries as you want. I only registered 4: Egypt, Ethiopia, Kenya, and Nigeria. So as you may have guessed, it's based on Nigeria having the highest population, the largest in Africa, Ethiopia having the second largest, and Egypt the third. Kenya only because they're our neighbor. So I'll click Ethiopia first. And you're treated to a buffet of data files for Ethiopia, okay, going all the way to year 2000 in 5-year increments in this case to 2005, and then 6-year increment 2011, 5-year again 2016, 3 years 2019, 2 or 3 years 2021 and 22. My interest is the 2016 data, which I have already downloaded. So I'm not going to click here. What I'll show you how to download today is the GPS data set. GPS data set. So click here, because today's presentation, the three-part presentation, is about spatial statistics, the GPS, Global Positioning System. So click here. And by the way, the files come in 5 different formats. There's the stata version, there's the all flat file version, the SAS file, SPSS, and all hierarchical. And these are the files: the birth recode, couples record, fieldwork questionnaires, household recode, individual recode, children's, men's, and household member record. For today's presentation, the file I'll be using would be the household recode and individual women's response recode. And the third one would be the geographical data. So I'm going to click these two and click download file. It's processing. And you go over here. Okay. The data I asked for is here. ET 2016 DHS 0304 as a zipped file. And I'm going to open it. And I'm allowed to choose a destination. I'm going to save it or extract it to my D drive. Under that, DHS 2016. Under that, I created a folder named ACIPH. You probably remember what this stands for. Okay. And the map data is here. Okay, and those are the two. And now, that's how you download it. And next, we'll see how to. We will next see how to bring in the data into your PC environment using R programming. So I'm going to fire up R. RStudio. First thing I'm going to do is clear the console. Control L will do that for you. And then clear the environment. Yes. So this is the editor window here, the console here, the environment here. Here is where the files are and the plots are displayed, or where you'll find a list of packages. Okay, so we'll go to the editor window. We're going to start here. Morse recording. A hash represents a command that has been commented out, meaning the software will not be able to run it, meaning you don't want the software to run it. Okay. So the first thing we're going to do is set our directory. So for that, we come to here, Sessions, set your directory, choose your directory, D drive, DHS 2016, ACIPH. ACIPH. So that's a destination for all of the results from today's R programming session. And sure enough, we have our directory set here as D drive, DHS 2016, and ACIPH. Okay. Next step is to bring in packages. The packages I would like to bring in are, in particular, the Pacman, which is a suite of packages. And within that, we will have a package called Party Psych, but we're particularly interested in Rio and Tidyverse. Rio and Tidyverse. Rio is the best, one of the best packages for bringing in external data. So I'm going to load library dataset. Okay. I'm going to load the library foreign. That's, again, a package needed to bring in external data. So the first command I'm going to use is the read.data command. This is an assignment operator, less than, with a dash. And I'm interested to look at all the files that I showed you earlier. First, let's just see how many variables we have in the birth recode. So I'm going to give you the file name, DHS 2016 birth. Okay. So I'm going to run this. Okay. So I just run this program, read data, assignment operator, bring it into this data file as the name, DHS 2016 births. Dimension, you can look at the dimension of that file by using the dim command. So the file has 41,000 rows, observations, and 1,287 variables or fields. And you can also see that here, right here in the environment. 41,392 observations and 1,287 variables. Now we're going to bring in the second file, the couple recode. For that, I gave it the name DHS 2016 couple. So run that. It's running here. Okay, that record file has 6,141 observations, fewer observations, but more variables, 2,582 variables. Next is the household file. The dimension on that, we will be using this file in today's presentation. This file has 16,650 observations, more observations than this, but fewer than the first. And it has 1,966 variables. Next is the main data file. This is our main interest here, because our topic of analysis is women's attitude, and this is the individual women's file. So let's run that. And the last file, women's file, has 41,392 observations and 1,287 variables. Okay, so we have brought in four data files. We'll be using the last two. The first thing we're going to do is data reduction. Data reduction with correction. The individual women's data file has 15,683 observations and 5,902 variables. That's a lot of variables, almost 6,000 variables, because our main file of interest has too many variables. First thing we're going to have to do is do a data reduction. Again, the first thing we're going to have to do is a data reduction. Somehow, for some reason, I am not able to tell whether the recording is taking place. It looks like it is taking place. Let's see. Yes, apparently it is taking place. So let's continue with our programming. Next step is data reduction. Reduce the data. Let's see. Data reduction, so reduce the data. So we're going to create a reduced data file. Here, let's start with the women's record. Create a new file using the GIS 2016 underscore WOM, DHS 2016 underscore WOM, and give it a name, reduced. Assignment operator, so DHS 2016 underscore WOM pipe, select the following 1, 2, 3, 4, 5 variables. Variable, first one is sampling cluster, number, this one is region number, weights, education variable, and the wife beating variable. As I shared earlier, wife beating was asked under 5 different scenarios. I only considered one scenario, which is if she argued with the husband. Is it okay for a husband to beat his wife if she argued with him? Pipe that into print so we can see the results. So let's run this, see what happens. So we now have 15,683 observations and only 5 variables. So we were able to reduce the number of variables from 5,902 to just 5. If we were to run the dimension command, you now have only 5 variables. So the next step the next step is to create a cluster frequency table. Create a cluster frequency table. Okay. And based on the proportions of women who said yes or no to V44C, is it okay for a husband to beat his wife if she argued with him? And we will save the result as CSV. We will save the result as CSV. We'll try and override. Okay, unweighted prop. Let's call it M1 here. Okay, so first let's create a frequency table. And print it. Okay, so these are the frequencies. In cluster number 1, 26 women were interviewed. 3 said no to the question, is it okay for a husband to beat his wife if she argued with him? 3 said no. 23 said yes. So an overwhelming majority said yes. In cluster number 2, you have a totally different situation. Out of a total of 13, 7 said no. Okay, so the majority said no. 4 said yes. 2 said they didn't know. Okay. Now let's turn these numbers into proportions. For that, we're going to run this command, prop.table, cluster frequency of the wife beating variable WB. Now you have proportions. In the first cluster, 11.5 is what it will turn into in terms of percentages. Said no. 88.5 said yes. In the second cluster, the majority, 53.8% said yes. 30.1%, 30.7% said no. 15.3 said I don't know. Now let's turn this into comma separated value tables, CSV, and we're going to give it the name unweighted, cluster level, wife beating proportions. This is the month of March, so I added M, and this is the first file we're running. So let's run that. Control. Okay. Let's see if we can find this CSV file. So let's go here. D directory. DHS 2016. by date modified. So the latest CSV file created was today, March 4th, 2:32 p.m. California time. And these are the proportions turned into CSV. Let's open it. Okay, let's add the word cluster number here. So these are the proportions you saw for cluster 1 and proportions you saw for cluster 2. Save that. Okay. Now let's return to our programming. Let's do that for regions. Regions, and actually did that already. A region level. In two ways. For region level and for cluster level. By the way, the example I just shared, those are unweighted proportions. Now we're going to do some weighting. To do weighting, we need a library called questionnaire. So let's load that library. Okay, now we're going to create a new file name, weighted cluster level Y beating. Okay, these are the commands. Assignment operator, wtd.table, and you get the variables from the reduced table. In particular, bring in the cluster number and women's responses, and add these weights, okay, V005, and the DHS recommendation is to divide the weights by 1,000,000. Okay, so let's run this. These are the weighted numbers. In terms of proportions, I was asked during the presentation whether I had weighted the cluster percentages that I used in the study. I said no, but I had no certainty that not weighing the values had any impact at all. I'm happy to report in this presentation that weighting would not have made a difference because the proportions at cluster level remain the same. The proportions at cluster level remain the same. So we're going to write this weighted proportions as CSV. So this is a file name, weighted. Let's add March, M, and number 1. And let's go find the weighted proportions. Yep, right here, weighted. Weighted proportions are the same. It was 11.5 versus 88.5, 53.8, 30.7, 15.3. That's exactly what it was, weighted. So unweighted, weighted, unweighted did not make a difference. Cluster number. So similarly, I run weighted and unweighted at the region level. Okay? Weighted, unweighted at the region level. And the result, at the region level, it appeared on the surface that there is a difference. So, weighted region, let me open this one. At the region level, this was the unweighted yes. These are the unweighted yeses. Tigray, Afar, Amhara, Oromia, Somali. And these are the weighted percentages. Okay? Not that different in Tigray, but different in Afar. Unweighted was majority yes. Weighted, it was not majority yes. Okay. So not much difference here or here. There's some difference in Somali, 0.32 versus 0.30. Not much difference here. Not much here. There's a difference in Gambela, 0.4 versus 0.36. Harari, not much difference, and not much difference. Dredawa, some difference. And then, do these differences really matter? Are they statistically significant? So I did a t-test using this formula here. Okay. And it's not statistically significant at 95% confidence. That's one-tailed. And it's not statistically significant at 90% confidence, the two-tailed. So it appeared to be different, weighted versus unweighted at region level, but not statistically different. And there was no difference at all at the cluster level. Okay. And in this way, I brought in data. So next was using the household recode variable, because I wanted to bring in some household level variables. And so first thing I did was to reduce the data, because the household variable had 16,000 observations and 1,966 variables. I just wanted to bring in a few. So I brought in just these ones here. Okay. It has to do with water source, type of toilet, type of electricity. I mean, whether they had electricity, yes or no. Whether they had a radio, yes or no. And later on, I also brought in wealth index. Okay. and save them all to that same folder over here. For example, this is weighted cluster level ownership of radio over here. So this is ownership of radio, yes versus no at cluster level. Yes versus no at cluster level. And similarly for toilet, type of toilet and water source. Okay, flush toilet and other types of toilet. These are all weighted. Electricity and also wealth index, weighted by cluster level. Proportion in the lowest fifth, second fifth, middle fifth, fourth fifth, and the best fifth. Okay? I will be sharing, I'll be copying these to Word and then create a PDF, and I'll be sharing this online. And this brings part 1 of my video presentation to a close.